So before we get started, there's a couple of different ways that we want to remind ourselves for solving quadratic equations. So there are many different methods. So we're going to start with the first method is the factoring method using either the PQ or AC method. Then we also have another method called completing the square. And then we're going to get to the final method that we're going to talk about for solving quadratic equations, which is the quadratic formula. So we'll get to all of these as we go forward. So the first method we wish to talk about is factoring. So to use factoring, one thing we need to remember is what is called the zero product rule. And we're going to use this a lot throughout the semester. And the zero product rule says if A and B are any algebraic expressions, and A times B is equal to 0, then the following must be true. Then A equals 0 or B equals 0. So the zero product rule says that the only way you can multiply two things together and get the number 0 is if at least one of those two things is 0, right? So we're going to combine that with our factoring to resolve our first example. So in general, in order to factor a quadratic trinomial, what we're going to need to do, so the first step is always to get it in standard form. And just to remind us, standard form is where we have one side equal to 0. So something of the form ax squared plus bx plus c is equal to 0. In our example, our quadratic trinomial is not in standard form because we don't have 0 on one side. To convert this to standard form, we would subtract 30 from both sides of the equation, and that gives us x squared minus 7x minus 30 is equal to 0. So now, step 2 is we're going to need to factor. And there are many, many different ways of factoring. For this one, we're going to use our PQ method, which states we need factors of C that add up to B. Of negative 30 that add to negative 7. So we could make our factor list for negative 30. So we have 1 and 30, 2 and 15, 3 and 10, 4 doesn't work, and 5 and 6. But since the product is negative, it means one of our factors has to be negative. So in our case, that means we're going to have this, and we would have negative 10 plus 3 is equal to negative 7, which is exactly what we wanted, which is this coefficient. So that's our P and our Q, so this factors into x minus 10 times x plus 3, which is equal to 0. So then step 3 is we're now going to use our zero product rule. And we identify our A and our B in this case. So our algebraic expressions for A and B are, here's our A times B equals 0. So our A in this case is going to be x minus 10, and our B in this case is going to be x plus 3. So by the zero product rule, we get the two equations, x minus 10 is equal to 0, or our equation in B is x plus 3 is equal to 0. And then we resolve each of these separately. So we add 10, and we get our first solution is x is equal to 10. and we minus 3 and we minus 3, and we're going to have x is equal to negative 3. All right. We can then check, and this step is completely optional, but we have our two solutions, and we can always check by going back to the original equation. So if we grab our graphing device, we could put in our different values. So we have x squared minus 7x equals 30. So x squared minus 7x would be 10 squared minus 7 times 10. And we're supposed to get 30. So let's double check when we press enter. Indeed we do. And we can check our other solution, negative 3. So negative 3 squared minus 7 times negative 3 is also equal to 30. So we verify that we indeed solved that quadratic equation correctly by factoring. And as I mentioned, the check step is optional. You don't have to check. But it can make your life a little bit easier. And also verify that we got the correct answer. So factoring is when we, by whatever method, we set the quadratic equation equal to 0, we factor, and then use the zero product rule in order to resolve those two linear equations that we get. So that's our first thing that we're going to remind ourselves of. The next one we want to talk about is the square root property, or the square root principle. So the square root property states the following. If A is any algebraic expression, and A squared is equal to B, then we get the following. A is equal to the negative square root of B, or A is equal to the positive square root of B. And it's worth noting that, this is often shortened to A equals plus or minus the square root of B. The reason I mention that is people will often use the square root property and forget the negative square root. They'll only give one of the two solutions. So just be aware that when you use the square root property, unless B is 0, you will always get two solutions, one positive and one negative. All right. So now, armed with our square root property, let's take a look at example number 2. So we wish to solve x minus 4 squared is equal to negative 5. So we want to use our square root property. So once again, we identify our A and our B. So in this case, it looks like our A is going to be x minus 4, and it looks like our B is going to be negative 5. So then, according to the square root property, we get that A is equal to the negative square root of B. Oh, I shouldn't have been writing A. A is x minus 4, so let's put in the right values. And B is the square root of negative 5, or our other solution, or our other equation, we haven't solved yet rather, is x minus 4 is equal to the positive square root of negative 5. So we then need to resolve each of these equations. So thinking back to last time when we did complex numbers, if we have a negative underneath the radical, when this simplifies, it simplifies to an I, so we get the negative square root of 5 times I, and equals to x minus 4. And on this side, we get the same thing, but we're going to get the positive square root of 5i. And then to resolve each equation, we add 4 to both sides, getting our complex numbered solution, 4 minus the square root of 5i. And adding 4, and we get x equals 4 plus the square root of 5i. So we got 2 complex numbered solutions to this quadratic equation. And it's worth noting the solutions are conjugates. And when you get complex solutions to a quadratic equation with real coefficients, they will always be conjugates of each other. So we have 4 minus 5, or square root of 5i, and 4 plus the square root of 5i. And that will always happen when you get complex or imaginary solutions to a quadratic equation. So once again, let's check. So we can use our calculator once again, and remember, we need to make sure that our calculator is in complex mode, not real mode, or it'll give us an error. So we change it from real mode to a plus bi mode. If you did that last time, or if you did it for your homework, which would have been a good idea, it'll stay that way until you tell it otherwise. So we go x, and we have, I'll check one of them, x is equal to 4 plus the square root of 5. And remember, our I key is secondary function on the decimal point on our calculator. So that's all the way down here at the bottom of our calculator. On the decimal point key, we have the secondary function for I. The other thing we want to take note of is don't put the I under the radical symbol. That will mess things up 100% of the time. The I never goes in the radical. So we have our x, and then we're plugging into our equation, so minus 4 squared. And if this really is a solution, when I press enter, what should I get? Negative 5, right? So I press enter, and indeed, it shows that the solution to that equation is 4 plus the square root of 5i. And if you wanted to check your other solution, they're conjugates, right? If you want to pull up what you typed on the previous line, press your second key and then press enter, and it will pull up what you typed, and then you can just go back in and edit it. Silly touch screen. And you just go back. And we change it from a positive square root of 5i to a negative square root of 5i. We press enter. And indeed, it does confirm that that is also a solution. So once again, our quadratic equation had 2 solutions. This time they were a complex conjugate pair of solutions to that equation. So remember, we can use our graphing device to do calculations with complex numbers just like we can with real numbers. And I know if you took the prerequisite course, Math 121, they made you do all this stuff by hand. I know that we've all done this before. That's why I don't want you doing this stuff by hand. Just use your calculator. That class was to make sure you knew how to do it. This class, we're going to have enough other stuff. We're going to need to know how to use our calculator to outsource some of this stuff, or it's going to just make our homework and our assignments too much work. So we need to use our calculator when we can, as we will discover. All right. So now, so the first thing we're going to need to do to resolve this is to isolate our perfect square. So we minus 1, and we get 2 times x plus 3 squared is equal to 8. We divide by 2, and we get x plus 3 squared is equal to 4. And we identify our a and our b. So then by our square root property, we get a is equal to the negative square root of 4, and a is x plus 3 in this case. And we also get x plus 3 is equal to the positive square root of 4, which is 2 in both cases. So we get x plus 3 equals negative 2, or x plus 3 equals positive 2. Minus 3 to get us x is negative 1. We minus 3, and we get x is negative 5. And that would be our two solutions to that equation. And if we wanted, we could go back and check them by plugging them into the original. All right. So now the next thing we want to talk about is an algorithm that is interesting and definitely has some uses, as we will see. And it is called completing the square. So we wish to complete the square on x squared plus 6x minus 16 is equal to 0. So we're going to look at this in terms of the geometry of the situation, because that's where the name comes from. This algorithm was known to the ancient Greeks a couple of thousand years ago, and in fact they resolved all of these types of equations geometrically as opposed to algebraically. So the idea behind completing the square is the following. When we say x squared, we literally would visualize a square that had side length of x. If that were the case, its area would then be x squared. Then if we wanted to visualize x, x would be a rectangle with width 1 and height x. And 6x would mean we would have 6 of these 1 by x rectangles. And the constants we're not going to worry about, and in fact we're going to take our equation out of standard form by adding the 16 to the other side. And we'll see why in a minute. So we now have our x squared plus 6x, and the goal of completing the square is to literally build the largest square using those pieces that is possible. So if we're going to build a square, let's start with our square piece that looks like this, that we know has side length x. Well, the property that makes a square as opposed to a rectangle is that its length and its width must be equal. So if I have 6 green rectangles and I'm trying to build a square, how many rectangles should I put on each side of this square? Well, could I put 4 of them here and 2 of them here? The answer is no, because if I did that, that wouldn't be a square, right? One side would be longer than the other. I'd be building a rectangle. So in order to build a square, I have to put the same number of rectangles on each side of this square, and they would have to align on the x side to do this. So then each of these would then be 3. Well, then that would make the entire side of each of these x plus 3, right? The reason this is called completing the square is now if I look down here, I don't actually have a square. I'm missing some parts right here. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I am missing 9 pieces right here in order to build a square. So to complete my square, I would have to add 9 blocks. But if I add 9 blocks to one side to keep it balanced, what would I have to do? Add 9 more to the other side. So in terms of our equation, it would look something like this. X squared plus 6x is equal to 16, but then we need to add 9 pieces to both sides. We could then factor the left-hand side, and we'll notice if we did, what are our factors of 9 that add up to 6? Well, 3 times 3 is 9, and 3 plus 3 is 6. So this would actually factor into x plus 3 times x plus 3. Well, wait a minute. Where have we seen that before? That was the side length of the square that we actually created, right? We created a square with side length x plus 3 and x plus 3. So this polynomial on the left side actually geometrically represents the area of this perfect square that we built. It's 25, because 16 plus 9 is 25, but anything times itself is that object squared. So notice, after completing the square, we've turned this into the problem we were just solving. This thing is now vulnerable to the square root property. So we can solve by using the square root property. So in this case, we would have our a and our b, so we would end up with x plus 3 equals the negative square root of 25, or x plus 3 equals the positive square root of 25. And the square root of 25 is 5, so x plus 3 equals negative 5, or x plus 3 equals positive 5. I have a typo there, x plus 3. We minus 3, we minus 3, and we get x equals negative 8, or minus 3 and minus 3, we get x is equal to 2. So geometrically, that is the idea of how completing the square worked. So in our next example, we will actually write down the algorithm that we just did here, and we'll go back and reference this picture to help us determine exactly how that algorithm works. So let's take a look at our next example. But before we get started on this example, once again, we want to do a little comparing and contrasting. So in the previous example, it was pretty simple because our a coefficient, or the number in front of the squared term, was 1. So we actually only had one red square. In the example that we're looking at, it's going to be a little more complicated because we have a 9, but that's not really going to be a problem. So let's go through and outline the general steps for completing the square. So step 1 is we are going to isolate the ax squared and bx term. So essentially, the first thing we're going to do is we are going to move any constants to the other side of the equation. And that gives us 9x squared minus 6x is equal to negative 46. Step 2 is if a does not equal 1, divide the equation by a. So this has the effect of what we saw above to turn it into having only one red square. So in our case, our a value is 9. So we're going to divide everything by 9 in order to get the x squared coefficient to be 1. So that leaves us with x squared minus 6/9 reduces to 2/3 is equal to negative 46 over 9, and that doesn't reduce at all. So now, let's go back to our picture and see what we did next. So after we had something in this form, we drew a picture, and what did we do? We put half of our blocks on one side and half of our blocks on the other. We'll notice that in this, the number of blocks that we had is actually our b coefficient. So in this example, we had 6, and half of 6 is 3, so we put 3 on each side. So now, in our problem, we identify our b as negative 2/3, so what we're going to do is calculate b divided by 2. So for us, that's negative 2/3 over 2, which is negative 2/3. And if we write 2 as a fraction, it's 2 over 1, so then we would multiply by the reciprocal, and we get negative 1/3. Okay, so that's how many blocks we added, but that's not really what we needed to do to finish completing the square. So we needed some constant terms because we needed to add our missing pieces. Well, in the previous example, we added 9, and we'll notice, well, the 9 was the area of the blue square that was missing down here. Well, we could have gotten that number instead of just counting them like we did by we added 3 here and 3 here. Well, what's the area of this square then? 3 times 3 is 9. So the number of pieces that is missing will always be b over 2 squared. So we have our b over 2. We calculated b over 2, and then we square b over 2. So that gives us that we're going to have negative 1/3 squared. And a negative times a negative is a positive, and 1/3 times 1/3 is 1/9. So then we get 1/9, and we're going to add it to both sides of the equation. So then we end up with x squared minus 2/3 x plus 1/9 is equal to negative 43 over 9 plus 1 over 9. All right, so then what did we do next? Well, up here, we then factored and simplified. So now step 4 is we're going to factor and simplify. All right, so there was a typo when I went down this line right here. I had a negative 46, and for some reason my brain had a glitch and I wrote 43. So make sure to change this to negative 46, and then this should also be negative 46. So then, now we need to factor our left-hand side. And you're probably looking at this saying, well, that's going to be a little difficult with all those fractions. But our picture actually tells us what it's going to factor into every single time because we built this square. So in fact, what was the number of rectangles that we put on each side? It was always b over 2, which we calculated in the previous step. So our b over 2 was 1/9, and in this case it's positive. So it's going to factor into x plus 1/9 squared is equal to negative 46 over 9 plus 1/9 is equal to negative 45 over 9. And as I mentioned, we should note that this is always x plus b over 2 squared. So then we simplify that up and we get x plus 1/9 squared is equal to, and 9 goes into 45 5 times, so we get negative 5. So now finally, using our square root property, and I'll use the short form this time, we get x plus 1/9 is equal to plus or minus the square root of negative 5, which is going to be 5, and since the square root of a negative number is imaginary, we change the radicand to positive and pull our I outside. And then we subtract 1/9, subtract 1/9, and we get the two solutions, negative 1/9 plus or minus the square root of 5i. And notice, once again, the solutions to this equation are complex conjugates. So before we move on to the quadratic formula, a couple of notes about completing the square. Unless you are explicitly told to solve a quadratic equation by completing the square, I would never choose this algorithm ever. Completing the square has its uses. It is not very useful for solving quadratic equations. So you're probably asking yourself, well then why the heck are we doing it at all here? Well, it's a skill we need to learn because we're going to use it to do other things, and this is just a place where it happens we can practice it. But as far as solving quadratic equations on a quiz or a test, I would never complete the square. If you can't factor it immediately, then I would go to what we're going to talk about next, which is the quadratic formula. And we're going to see why in just a moment. All right, so the next thing I want to talk about is the quadratic formula. So first of all, what is the quadratic formula? So that's a good question. I know people have different songs and different mnemonics that they use to help themselves remember where this formula comes from, right? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Kind of seems like it's just this random thing, right? Turns out in mathematics, unless you're talking about probability, nothing is random. So where does the quadratic formula come from? So what I'm going to do right now, I think everyone should see at least once in their life, but I would never ask you to reproduce it. So if you want to sit back and relax for a second and watch what's happening, it's very informative, and I'll tell you again when you should start writing. But the idea of the quadratic formula goes back several thousand years to an Arabic mathematician named Al-Khwarizmi. His math book was discovered in Europe in the Dark Ages and helped bring Europe out of the Dark Ages. He actually had resolved all of these problems and a bunch of other things. And what he had done is the following. So he looked at this in a very different way. Instead of solving quadratics one at a time, he asked the bigger question. How can I solve every quadratic equation at once? So his goal was to solve this equation in general, ax squared plus bx plus c is equal to 0. And the way that Al-Khwarizmi did this is he used the completing the square algorithm. So the first thing he did is he divided everything by a, and that gave us x squared plus b over a x plus c over a equals 0. He then subtracted c over a from both sides, giving x squared plus b divided by ax is equal to negative c over a. So then to complete the square, you take half of your middle term and you square it, so that's b over a divided by 2, which is 2 over 1. So that's b over a times 1 over 2, which is b over 2a. And then he squared b over 2a, just like we did in our completing the square, and added it to both sides. So we have x squared plus b divided by ax plus b squared over 4a squared is equal to b squared over 4a squared minus c over a. So then in order to simplify, he needed to collect his like terms, and so he needed to get a common denominator. So on the right side, he needed to multiply the top and the bottom of our second fraction by 4a. And then remember, this always factors into our b over 2a, which is this piece right here. So we're going to get x plus b over 2a squared is equal to b squared, c times 4a is 4ac all over 4a squared. And as we notice, it's starting to come into focus here a little bit. If we use our square root property on both sides, we then get x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac, all divided by the square root of 4 is 2, and the square root of a squared is a. So then, finally, solving for x, we minus b over 2a, and we minus b over 2a. So we get x is equal to, and luckily these already have a common denominator, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So this is what we're going to need to write down. So the quadratic formula solves ax squared plus bx plus c is equal to 0. And the formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So at the end of the day, the quadratic formula is just an extension of completing the square. This is the other reason why you never want to complete the square. Somebody already did it on a generic quadratic and solved all of them at once. That's where this formula came from. So there's nothing mystical or magical about the quadratic formula. It's just completing the square that has been done on a generic quadratic. All right. With that said, let's go ahead and resolve example number 5. And example number 5 may look familiar. This is the example I did above when I used completing the square to solve. We'll notice that resolving it using the quadratic formula is going to be much, much simpler. So the first thing we need to do is identify A, B, and C. So our standard form is ax squared plus bx plus c is equal to 0. So our A in this case is going to be 9. Our B in this case is going to be negative 6. And our C is going to be positive 46. So then we just put all of this into the quadratic formula. So we evaluate the quadratic formula. Which is, remember, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in our case, that's going to be negative 6 plus or minus the square root of negative 6 squared minus 4 times our a, which is 9, times our c, which is 46, all divided by 2 times a. So from here, we just need to simplify that. So let's grab our graphing device. And let's start putting our values in. So I'm going to start with the radicand, which is negative 6 squared minus 4 times 9 times 46. Press enter and I get negative 1,620. So that gives me negative 6 plus or minus negative 1,620 all over 2 times 9 is 18. And then I need to start simplifying this. So remember, we can use our calculator to help us simplify those large radicals by going 1620, and then we go divided by x squared, and we go second table, and we can scroll down in our table until the y column is less than 2. So here, and then we have to scroll back up until we find the first whole number. So we go back here in the y column, we keep scrolling up, and there we go. So we find that the first whole number in the y column happens right here. So then remember what that does is it tells us that this, so it's negative, so we're going to get an I on the outside. And remember, the x is what comes out of the radical, and then the square root, the y column tells us what's stuck on the inside. So we're going to have that our 5 is what was stuck in the radical, and the 18 is what came out of the radical, and then all of this over 18. So then we keep simplifying. We get negative 6 over 18 plus or minus 18 square roots of 5i over 18. Those reduce out. Negative 6 over 18 is negative 1/3 plus or minus the square root of 5i. And we'll notice, after all that, we get exactly what we got back here. All right, awesome. So, with that said, it's now. All right, so let's go ahead and resolve this. So let's identify our A, our B, and our C. So our A is 1, our B is negative 6, and our C is 18. So something else that we can do with our calculator, which is kind of cool, if we go back to our home screen, we have our A, our B, and our C, right? So we can go 1 on our calculator, and if you press the button just to the up left of 1 on your calculator, it says STO. And it'll make a little arrow, and then if you press alpha and the key just below it, you can save A as 1 in your calculator. And we can do the same thing, negative 6 alpha B, oops, forgot my store button, alpha B. And then I can go 18 store alpha C. So now I have this, and if you have a color version, remember you can just go, make your fraction bar and type in the quadratic formula directly. If not, you have to do it the long way because you may get complex numbers. So then our quadratic formula is negative b, and then I go plus the square root of b squared minus 4 times a times c, close my parentheses, divided by parentheses 2 times a. And remember, when you're doing this on the black and white calculators, you have to put parentheses around the numerator and denominator, or your calculator will lie to you. If you're using one of the C's or the CE's, you can just do the alpha y equals and type it just how it looks, and it'll work out. Press enter, and what does your calculator tell you the solution is? 3 plus 3i. And if you wanted to get the other solution, you could press second enter and go back and edit the formula. And instead of plus, you would get the minus, but you don't even really need to do that, right? Because we got a complex solution, and what do we know? That they're always conjugates. So if one solution was 3 plus 3i, what would the other solution have to be? The conjugate, which was 3 minus 3i. And indeed, our calculator thought that was the case and gave it to us, right? So we can store those values, and that can be really helpful. One thing, this works great when we have whole numbered solutions, even if they're imaginary. If you get irrational solutions, it's going to give you some ugly decimals. That can be a problem. Something else that is helpful is sometimes you get decimals, but they're actually fractions. So if you're not sure, so like if you had 0.0625, you may not know what that is as a fraction, but if you press your math key and then choose choice number 1 for fraction, it will convert that into a fraction for you. So your calculator can convert between fractions and decimals, and it does so under the math menu where we have frac and decimal to convert back and forth between those two things. All right. So some nice things that we can do with our graphing device. The next thing we wish to speak about is called the discriminant. So the discriminant is the expression under the radical in the quadratic formula. So specifically then, the discriminant is the b squared minus 4ac. So the discriminant tells us about the nature of the solutions to a quadratic equation. So we have three possibilities when it comes to the types of solutions that a quadratic equation has. So the possibilities are, if I have b squared minus 4ac, and it is a positive number, when we take its square root, we're going to get the square root of two positive numbers. So in terms of our calculator, we're going to get something that looks like this if we did a graph. And that would show that we would get exactly two real solutions. Our next possibility is that our discriminant b squared minus 4ac is exactly equal to the number 0. If that's the case, it would mean our parabola would look something like this, where it comes down and its vertex is exactly on the x-axis. So this would have one real solution. Sometimes this is called repeated real solution. So if you ever hear that, it means the same thing. A repeated real solution is the same as one real solution. The last case, and this is where the misnomer for imaginary numbers came from, is it's entirely possible to have a quadratic or a parabola that comes down, it has its vertex and turns around and goes back up, and it never touches the x-axis. Well, mathematicians in the 16 and 1700s knew that solutions were the same as the x-intercepts of a graph. Well, that quadratic does not have any x-intercepts, therefore it had no solutions. So when people started discovering the idea of complex numbers and finding complex solutions, they didn't call them complex at first, they called them imaginary, and it was used as a pejorative because you couldn't see it. They were basically mocking people for calling them solutions. But the funny thing is the joke's on them. Complex numbers are two-dimensional. If you have a two-dimensional object and another two-dimensional object, when you combine those, that's 4 dimensions. To see the x-intercepts, you would have to be able to draw a 4-dimensional picture. And they exist, and they are just as real as any other type of number that you can imagine. And if you like things like electricity, you really like complex numbers because that's how it works. You need to balance certain things in the complex plane to keep our alternating current in phase. Otherwise, things start on fire, and that's not a good thing. So complex numbers aren't imaginary, and like I said, it's a misnomer that came from this. And this happens when we have negative discriminant. So if this is less than 0, we get 2 imaginary solutions. So we can use the discriminant to classify the number and type of solutions to a quadratic equation. That is not the right example. So we want to find the discriminant and then determine whether it has one real solution, 2 different real number solutions, or 2 different imaginary solutions. So this works very similar to what we did with the quadratic formula. So we have A is 25, B is 20, and C is 4. And we calculate B squared minus 4AC, which is going to be 20 squared minus 4 times 25 times 4. So we have the following: 20 squared minus 4 times 25 times 4, and that gives us 0. So then we look at our 3 possibilities. If b squared minus 4ac is 0, we have 1 repeated real solution. And that's going to be it. All right. Let's go to example 7. So an open box is made from a 10 by 20 centimeter piece of tin. The box is formed by cutting a square from each corner and folding up the sides. If the area of the base is 96 square centimeters, what is the length of the removed square? All right, so let's label what we know on our diagram. So we have a 10 by 20 centimeter piece of tin, and we're forming a box by cutting each corner to make a square, and we're removing a square of side length x from each side. We're told that the base after we do this is 96 square centimeters. Well, if that's the case, if this whole side was 20 centimeters, and I'm cutting out an x from each side, then this has to be 20 minus x. We get something similar here, where that side is going to be, minus 2x, because we're cutting out 2 x's. We get something similar here, because we cut an x here, and we cut an x here, so that would be 10 minus 2x. So then that gives us the length and the width of the base's rectangle, and we know that our area formula for a rectangle is length times width, and we know its area. So we get 96 is equal to 20 minus 2x times 10 minus 2x. 20 times 10 is 200. 20 times negative 2x is negative 40x. Negative 2x times 20 is negative, or times 10 is negative 20x. Negative 2x times negative 2x is positive 4x squared. Equals 96. Now we collect our like terms. So we get 4x squared minus 60x plus 200. We minus 96. We minus 96. And we get 0 equals 4x squared minus 60x plus 104. Well, let's try this again. We're still going to factor. So we factor out our GCF in this case, which this time is 4. And we get x squared minus 15x, and 4 goes into 104 26 times. So now we factor, our factors of 26 are 1 and 26 and 2 and 13. And so we're going to get these two. So it factors into 4 times x minus 2 times x minus 13. So we get two solutions. So we have x minus 2 equals 0, or x minus 13 equals 0. We add 2, we get x equals 2. And we add 13, and we add 13, and we get x is equal to 13. So in this case, we had two solutions, but reality tells us we need to reject the solution x equals 13. And if we go back and look at our original problem, what were the dimensions of the piece of tin? 10 by 20. Can you cut something that is 13 centimeters out of something that is only 10 centimeters in height? The answer is no. So this doesn't make sense in reality. So you might be wondering then, well, why did math lie to us? Why did math give us this answer? And it's actually not math's fault. Math gave us exactly what we asked for. The problem is the universe we live in. I can't be negative 4 feet tall no matter how much I want to be, right? In fact, what's the smallest distance that can exist in our universe? 0, right? It doesn't make sense to have negative distance. But if we take that solution 13 and you try to put it back into this original equation, what did we really ask for? We asked for two numbers that when we multiply them together, we get 96. If I put 13 in here, 2 times 13 is negative 26. Negative 26, so 10 take away 26 is negative 13. If I put 13 here, 2 times 13 is still negative 26. So I get 20 minus 26 is negative 6. Negative 6 times negative 13 is positive 96. Math says that two negatives, when you multiply, give a positive. That's what we asked for. If you check our other solution, which is 2, 2 times 2 is 4, gives us 10 minus 4 is 6. 2 times 2 is 4. 20 minus 4 is 16. Positive 16, positive 6. Oh, they're the other two numbers that give us positive 96. It's a product. So math gave us the two solutions, but our universe said that distance can't be negative. So it's not math that says we reject this. It's physics in the universe that we live in. All right.